In this example, we're going to work with not only looking at a normal distribution in general, but also figuring out calculating the z-score based on some questions, and also using that standard normal table, which is at the end of your note set. So birth weights. Birth weights of babies born in the US can be modeled by a normal distribution with a mean of 3,250 grams and standard deviation of 550 grams. Draw a sketch of this distribution. Remember, they don't have to be perfect, but what I would suggest is make sure you draw it clearly so you can see what's going on. The center is at 3250. A lot of times I will label this specifically mu so that I remember it's also what it is. This is the birth weight of US born babies in grams. You want to make sure you put your units if they're whatever unit is being used. That's helpful. And the standard deviation is 550. So in other words, this curve is approximated by the normal distribution with the center at 3250 and a standard deviation of 550. Now, babies who weigh less than 2,500 grams are classified as low birth weight. Shade the area corresponding to the probability that a randomly selected baby is low birth weight and make an educated guess of this probability. So I'm just going to, I will do this in red so you can see that. I know it's going to be down somewhere. I don't know exactly what, but I'm just going to draw it here. And I'm interested in what this probability is. And I'm going to guess, I don't know, I'm going to go with 15%. You can, whatever you guessed is fine. I just guessed 15. Now it says calculate the z-score corresponding to 2,500 grams. Also interpret what the z-score means. So remember, z equals our observation minus the curve center divided by the standard deviation of the curve. So that's going to be, the z in this case will be the 2,500 minus 3,250 divided by 550. And when you plug that into a calculator, you get negative 1.36. A lot of times students don't like to look at negative numbers, but remember, be careful with your signs. Make sure you put things in the proper order. Don't want to reverse y and mu because your sign will be wrong. And drawing a picture, honestly, it helps me see, oh yeah, because this is below the average, I expect to have a negative z-score. So what does this represent? It tells me that 2,500 gram birth weight is 1.36 standard deviations below the mean. So that's what that's telling me. It's telling me that that birth weight here is 1.36 standard deviations below the mean. Now, use this score and the standard normal table, sometimes called the z-table, to determine the probability that a randomly selected baby is of low birth weight. So this is when we're going to use the table. Remember, we're going to look for, we've got some information, and we want to know what this area is under the curve. So we want to know what is that area. So if you get motion sick, please close your eyes for a second. I'm just going to scroll down to the bottom here to get to the table. This is the standard normal probabilities table. It will be called sometimes the standard normal table, the Z table, lots of different ways that it's called. But remember, in any way, in any case, the Z is always going to be calculated the same, y minus mu, so your observation minus your center over the standard deviation of that curve. Whenever you get a table entry, it's always going to be to the left. It's never on the right side. It's the left side. Now remember, what's the total area under the curve? Hopefully you're thinking 1. I've said it a lot of times and I'm going to keep saying it. That way we can use the complement rule. If I know this area shaded in the gray that I just filled in, do I know the area in the white? Yes, it would just be the complement, 100% or 1 minus whatever the decimal is. All right. So we found that the z-score was negative 1.36. You're going to notice the first two values of the z-score are here. The second decimal point is up here. So we need to find negative 1.3. So here it is, negative 1.3. And then I'm going to go over to 6. So that's at negative 1.36. And I get 0.0869. So that is obviously in decimal format, hopefully at least obviously. If you know, remember at the center of the curve, it should be 50-50 split on either side. So if my z-score is 0, I would expect, 0.5. There's 0, 0, 0.00, and there it is. So let's go back up, and we're going to be using this table quite a bit more. This is just our first time through. So from the table, we get that that was 0.0869. So that's the probability that a randomly selected baby is of low birth weight. In other words, 8.69% of babies born in the US are classified as low birth weight. Remember to change a decimal to a percentage. We move the decimal over right twice. To change a percentage back to a decimal, we move it 2 places to the left, just as a quick reminder. Part E. Determine the proportion of babies who weigh more than 10 pounds, 4,536 grams at birth. This time, we're going to be looking, let's see, we've got our center at 3250, and we want 4,500, oops, let's try that again, 4,536 grams and weighs more than. So we know that we're going to shade this side. You notice I'm not doing really special charts here or really special drawings. I'm just trying to do a quick sketch so that I make sure I grab the right number in the end. So I'm going to first of all calculate my z-score at 4536 minus 3250 divided by the 550, and I get 2.34. I would expect a positive z-score because remember, right here would be 0, and anything going this way would be bigger because the y value is bigger than the mu. All right. Now, if I look at the table, I'm going to look up 2.34. So once again, close your eyes, scan fast. Let's see, we start with negative z, then we end up going to positive values, and we're going to go to 2.34. And we get 0.9904. But remember, the table entry is always showing the area below the z. Scrolling back up. So I know this area in here is 0.9904. Can I then find this area here? Certainly. It is going to be 1 minus 0.9904, which gives me 0.0096. So fortunately, as most mothers will tell you, it's nice that there aren't a ton of, over 10 pounds, that's a big baby. So hopefully this is making sense. We're taking this and we're standardizing it so that we can use the table. We standardize it by using the z-score. Describe another way you could have found the standard normal table, use that normal table to answer this question. Well, we know, remember, we moved this to 0 then, and we've got 2.34. So we know that this 4536 is 2.34 standard deviations above the mean. Remember, we want this area in this end of the tail, but if it's symmetric, would it be the same as the area in this tail? And the answer is yes, if we look at negative 2.34. So we could look at the other tail. I caution you to make sure that you are very careful when you do this, that you understand exactly what area you actually are looking for. So that's why I always draw pictures. If I look at negative 2.34, I'm hopefully going to have 0.0096. So once again, scrolling to the bottom, if I look at negative 2.34, look at that. I get 0.0096, the exact same value. Perfect. So we could have used symmetry. effectively. So that's one of the beauties of that bell curve. Now determine the probability that, this is for part G, that a randomly selected baby weighs between 3,000 and 4,000 grams at birth. So I'm going to quickly draw. I've got the 3250, and I want to know weighs between 3,000, I'll put 3,000 here, and 4,000 over here. So we want this area in between those two. Now we want to be careful. Some students will like, oh, well, I can just find one of them and then multiply it by 2 or something. Something easy like that. But is 3,000 the same distance from 3250 as 4,000 is? The answer is no. So the first thing we want to do is find both z-scores. So I'm going to find z sub 3,000. So that tells me that I'm specifically focused on this value. And I get 3,000 minus 3250 divided by the 550, and I get negative 0.45. Now the area under the table there is related to 0.3264. Please take a moment and make sure that you can find that area under the curve using the table. Okay. If you struggle with that, please go back and check the earlier, like rewind the video a little bit and watch. For z sub 4,000, I'm going to have you calculate that, but I'm going to tell you that the answer is 1.36. And it makes sense that it's positive because it's above the center. If I look at the table, I get 0.9131. Remember, the area under the curve is always the area to the left, okay? So this is the area we're interested in. Well, when I found this 3,000, remember, I was finding, if I look here, I'm finding the area 3,000 and under. Hopefully you agree with that. And we're interested in the area under 4,000. So I'm going to change colors here just so we can see it. What I'm interested in is this area here, I should say. But the problem is that we have what we have is the z-score for 4,000, and I'm going to change that to green here so we can see. Remember, this area is everything from here down. So to get the area specifically in red, what we want to do is take the area under the curve for under 4,000 minus the area under the curve for 3,000, because what will be left will be right in between the two. Remember, the area under the curve is that probability. So if we take the area under the curve for the 4,000 minus the area under the curve for less than 3,000, we get 0.5867. In other words, 58.67% of babies weigh between 3,000 and 4,000 grams. And that is this area right in between the two of them. Now, flipping it just a little bit, how little would a baby have to be among the lightest 2.5% of all newborns? Let's see. So we know the baby's going to be little. We want the lightest. So we don't want in the center. We want instead what's in the tail here. 2.5% would be 0.025. Remember what we talked about earlier about moving that. But we don't know what this value is. So the area under the curve, remember, that's inside the table. So we're actually going to go inside the table so that we can then look to the outside to get a z-score. And you may be saying, well, why? Well, we know z equals y minus mu over sigma. We don't know what the value for y is. We do know the value for our mu, because that's our mu right here. We know the value for our sigma, which is 550. So now we need z. So scrolling down again, we're going to look inside the table to find 0.025. Well, we know it's going to be a negative value because the z-score will be negative because it is less than the mean. So I'm looking inside 0.025. Let's see. 0.02. Oh, we're getting closer. 0.02. Let's see. 0.02. Oh, there we go. 0.025. Now to get the z-score, I'm going to go out to negative 1.9 and go up to 6. So this time I'm starting inside because I have that probability and then going outside to get the z-score. It was negative 1.96. Now you can do the algebra, solve for y, and y gives us 2,172 grams. What if you said, well, Sonia, I recognize that this would be, if I added this and the other tail would be 5%, so then I could use the blah, blah. Yeah, you could do it that way, but honestly, you could use that empirical rule, but it's honestly much easier to use the z-score. How much would the baby have to weigh to be in the heaviest 10%? So I want the heaviest 10%, so this is 0.1. We know once again our center is here, but we don't know what that weight is. Now, if we know this area, should we look up 0.1? And hopefully you're thinking no, because we want to know what's inside the table is here, 0.9. Please pause for a moment and see if and solve this for yourself and then come back and check your answer. So a couple things. You know that 0.9 is a pretty big probability. You want 90% because you want to be in the top 10%. So you want this, you're interested in being up here. So I need to find 0.9, remember, because that is the probability on the left side of the value. Now, here's the thing. If you go in here, you know it's going to be positive here. Your z-score, excuse me, will be positive. And I want to find 0.9. And you're going to notice there is no exact 0.9. So I'm going to choose what is closest. This is only 0.0003 away, whereas this is 0.0015 away. So this is closer. So that's how I got to the 1.28. 1.28. So we want to choose the number that is closest. So there was not exactly 0.9, but 0.8997 is very close. Please close your eyes if you get sick again. And then you do the algebra and you should come up with y equals 3954 grams.